The morning air in the Ardennes forest carried a peculiar quality on December the 16th, 1944. Cold, certainly. The temperature hovered near freezing. But there was something else in the atmosphere that morning. Something the German soldiers advancing through the snow-covered pines could not yet identify. It was the weight of assumption colliding with reality. The shells came without warning. Not the familiar whistle and crack of conventional artillery, the kind that gave soldiers a split second to dive for cover or press themselves deeper into their foxholes. These shells arrived differently. They exploded in the air above the advancing formations, 30 to 50 feet overhead, showering the ground below with fragments of steel moving at lethal velocities. German infantrymen who had survived years of combat on the Eastern Front, who had endured Soviet artillery barrages from Stalingrad to Kursk, found themselves facing something they could not understand. The shells were not hitting the ground and throwing up fountains of frozen earth. They were not detonating on contact with tree branches or buildings. They were exploding at precisely the height needed to maximize casualties among troops in the open. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. A Wehrmacht corporal, sheltering behind a stone wall near the Belgian village of Monschau, later told American interrogators that his first thought was that the Americans had forward observers positioned perfectly to time their shells. But that made no sense. The weather was terrible. Thaw and low clouds blanketed the Ardennes. Visual observation was impossible. And yet the shells kept exploding overhead with uncanny precision, as if guided by some invisible force that knew exactly when they were passing over German troops. Men who had believed themselves safe in foxholes discovered that depth offered no protection. The explosions above drove fragments downward, filling the holes that should have been sanctuaries. Soldiers who threw themselves flat found that lying prone provided minimal cover when the danger came from directly overhead. Bunkers reinforced with logs and earth, structures that had withstood conventional artillery fire, proved vulnerable to fragments that fell from above rather than impacting at ground level. What the Germans were experiencing, though they could not know it yet, was the combat debut of one of the war's most closely guarded secrets. The VT proximity fuse represented a fundamental shift in artillery effectiveness, a technology that would force armies to reconsider tactics that had been developed over centuries of warfare. But understanding what made this moment so devastating requires understanding what came before it, what the Germans expected, and why their assumptions about artillery warfare were about to be comprehensively shattered. Artillery in World War II was a science of prediction and timing. Every shell fired from a gun followed a ballistic arc determined by physics, by the angle of the barrel, the powder charge, the weight of the projectile, atmospheric conditions, and countless other variables. Making those shells explode at useful moments required solving a problem that had occupied military engineers for generations. Contact fuses were simple and reliable. The shell hit something solid, a mechanical striker compressed, a primer ignited, and the main explosive charge detonated. These fuses worked perfectly for destroying buildings, bunkers, or armored vehicles where the shell needed to penetrate before exploding. But against troops in the open or aircraft in flight, contact fuses had severe limitations. A shell that missed its target by even a few feet would bury itself in the ground or fly past harmlessly before detonating on impact with the earth, or simply failing to explode at all. Timed fuses offered more flexibility. Before firing, crews could set a mechanical timer in the fuse nose. The timer would tick down during the shell's flight, ideally detonating the explosive charge at a predetermined moment. When used for anti-aircraft fire, this meant the shell could explode in the general vicinity of enemy aircraft, filling the sky with fragments without requiring a direct hit. When used against ground troops, Timed fuses allowed shells to burst above the target, showering fragments downward rather than wasting explosive energy by detonating against the earth. But timed fuses demanded precise calculation and considerable luck. Gunners had to estimate the range to the target, calculate the shell's time of flight, account for wind and atmospheric conditions, set the timer accordingly, and hope that nothing changed between the moment of firing and the moment of detonation. Against aircraft, which moved at speeds exceeding 200 miles per hour and could change altitude or direction at will, timed fuses were exercises in statistical probability. Fire enough shells into enough sky, and eventually some would detonate close enough to damage or destroy the target. The numbers told the story. In the early years of World War II, anti-aircraft batteries firing timed fuse ammunition required approximately 20,000 shells to bring down a single enemy aircraft. Some estimates ranged as high as 100,000 rounds per kill. Even with improvements in radar-directed fire control, which allowed gunners to track targets more accurately, the fundamental problem remained. The fuse had to be set correctly before firing, and that meant predicting where a fast-moving target would be several seconds in the future. German doctrine reflected these limitations. Anti-aircraft batteries concentrated their fire into boxes of airspace, filling predetermined volumes with exploding shells in the hope that aircraft flying through those zones would encounter fragments. The method worked to some degree, particularly against large formations of bombers flying predictable courses, but it consumed enormous quantities of ammunition and required large numbers of guns to be effective. Against ground forces, timed fuses were used primarily for harassing fire or for attacking troops in the open where the exact detonation height was less critical. Forward observers could call in adjustments to the timing settings, walking the bursts closer to the target through successive corrections. But this was a slow process, and in fluid combat situations, targets often moved before corrections could be applied. The Germans entering the Ardennes in December 1944 carried with them assumptions built on years of combat experience. They knew what artillery could and could not do. They understood that in poor visibility, with clouds preventing aerial observation and fog limiting ground observation, American artillery would be less effective. They believed that foxholes and prepared positions would provide reasonable protection from conventional timed fire. They thought they understood the rules of this particular game. They were about to discover that the Americans had changed the rules entirely. The proximity fuse did not emerge from a single flash of inspiration. It was the product of years of research, beginning in Britain in the late 1930s and accelerating dramatically after the United States entered the war. The fundamental concept was revolutionary in its simplicity and staggering in its technical complexity. Instead of requiring gunners to predict when a shell should explode, the fuse itself would sense the presence of a target and detonate automatically at the optimal moment. British researchers, particularly William Butemant and Samuel Curran, had proposed the concept before the war began. A tiny radio transmitter in the fuse nose would emit electromagnetic waves. When those waves reflected off a target and returned to a receiver in the same fuse, the device would measure the signal strength. As the shell approached its target, the reflected signal would grow stronger. When it reached a predetermined threshold, indicating the shell was within lethal range, an electronic trigger would fire the detonator. The theoretical elegance masked extraordinary practical challenges. The fuse had to fit in the nose of an artillery shell, occupying the same space as conventional mechanical fuses. It had to survive being fired from a gun, enduring accelerations exceeding 5,000 times the force of gravity and simultaneously spinning at hundreds of revolutions per second. It had to operate reliably across extreme temperatures, from tropical heat to sub-zero cold. It had to resist moisture, shock, and the violent vibrations of high-velocity flight. And it had to do all this while containing a complete miniature radio system, including a transmitter, receiver, amplifier, power source, and triggering mechanism, all using vacuum tube technology from the 1940s. American researchers at the Applied Physics Laboratory at Johns Hopkins University and at the Carnegie Institution took on the challenge. They developed vacuum tubes that could survive gun launch, encasing the delicate glass envelopes in shock-absorbing materials and using planar electrodes that resisted the stress. They created miniature batteries that would activate only after the shell cleared the gun barrel, preventing premature detonation. They designed a thyrotron tube, a gas-filled switching device that could trigger the explosive train when the return signal reached the appropriate strength. The complete fuse contained approximately 130 individual components packed into a space smaller than a man's fist. A miniature windmill driven by air flowing past the spinning shell powered a generator that supplied electricity to the radio circuits. The transmitter operated at frequencies around 180 megahertz, sending out electromagnetic waves that reflected off any nearby object, whether an aircraft fuselage or the ground itself. Production began in late 1942 at the Crossley Corporation plant in Cincinnati, Ohio. By 1944, the American electronics industry had mobilized to produce proximity fuses on a massive scale. Crossley, RCA, Eastman Kodak, Sylvania, and numerous other contractors manufactured components and assembled fuses by the millions. At Sylvania's plant in Ipswich, Massachusetts, workers produced more than 5 million fuses, the highest output of any single facility. The cost per unit dropped from $732 in 1942 to approximately $18 by 1945, as mass production techniques improved and manufacturers gained experience. Over the course of the war, American industry would produce more than 22 million proximity fuses, a manufacturing achievement that ranked alongside the production of radar equipment and other complex electronic systems. But manufacturing the fuses was only half the challenge. Maintaining absolute secrecy was the other half. American military leadership understood that if the Germans or Japanese captured an intact proximity fuse and reverse-engineered its principles, they could develop countermeasures, or worse, create their own versions. The psychological impact on Allied air crews, who would suddenly face vastly more effective anti-aircraft fire, was considered potentially catastrophic. For most of the war, use of proximity fuses was restricted to situations where recovery by the enemy was impossible. The U.S. Navy began using them in combat in January 1943, when the cruiser USS Helena fired proximity-fused shells at Japanese aircraft attacking off Guadalcanal. 3 shells brought down a dive bomber that had just completed its attack run. The pilot never had a chance to report what had destroyed his aircraft. Naval use expanded throughout 1943 and 1944. In battles across the Pacific, proximity-fused anti-aircraft fire destroyed Japanese aircraft at rates that would have seemed impossible with conventional ammunition. Where time-fused shells required approximately 2,000 rounds to bring down a single aircraft, proximity fuses reduced that number to around 500. Against kamikaze attacks, where the aircraft flew predictable, straight-in courses, the efficiency was even higher. By mid-1944, proximity fuses had proven their worth against V-1 flying bombs attacking Britain. Anti-aircraft batteries equipped with proximity-fused ammunition destroyed buzz bombs at rates approaching 80%, compared to less than 25% with conventional fuses. The weapon's success against the V-1 threat convinced military leadership that the time for absolute restrictions had passed. But ground use remained forbidden. The Pentagon feared that a dud shell landing on enemy territory would compromise the secret. When the invasion of Sicily brought American artillery within range of Axis-held ground, special teams were dispatched to recover every proximity-fused dud that landed on the island. The restriction held through the summer and fall of 1944, even as stockpiles of proximity-fused artillery shells accumulated in depots across Europe. Then the Germans launched their Ardennes offensive, and everything changed. On December 16, 1944, the decision to use proximity fuses against German ground forces was made not in Washington or at Supreme Headquarters Allied Expeditionary Force, but in the pre-dawn darkness of the Ardennes by Colonel George Axelson, commander of the 406th Artillery Group. His unit was positioned to support the 38th Cavalry Squadron dug in around Monschau, Germany. And when German forces launched their surprise offensive that morning, the lightly armed cavalry troopers called desperately for artillery support. Axelson had the weapons he needed. His artillery group had recently received shipments of proximity-fused shells, marked with the code name WWII. The shells sat in ammunition dumps, ready for use. But official authorization to employ them against ground targets had not yet been granted. General Dwight Eisenhower, the Supreme Allied Commander, had been requesting permission to use the fuses for weeks. The Pentagon had resisted, citing security concerns. What if a dud fell into German hands? What if German scientists reverse-engineered the technology? Axelson made his choice. The emergency, he decided, trumped the restrictions. He ordered his gunners to load proximity-fused shells and begin firing. Minutes later, American 105mm howitzers started sending shells over the heads of attacking German infantry. The shells, their tiny radio transmitters detecting the ground below, detonated 30 to 50 feet above the snow-covered terrain. Fragments of steel, driven by high explosives, swept downward in lethal patterns. The effect was immediate and devastating. German soldiers advancing in formation found themselves under fire that their training and experience had not prepared them to counter. Foxholes that should have provided protection became death traps as fragments fell from above. Moving to new positions meant exposure to airbursts that could catch entire squads in the open. Even prepared positions, bunkers reinforced with logs and earth, offered limited protection as fragments found gaps and openings. 3 days later, on December 19th, Eisenhower formally requested clearance to use proximity fuses without restriction in the European theater. The request was granted on December 21st. By that point, the fuse had already proven their worth. Reports from forward units described German formations disrupted, attacks broken up, and counterattacks stopped by artillery fire of unprecedented effectiveness. 200,000 proximity-fused shells were shipped to American artillery units across the front. The Army had codenamed them POSI-T, continuing the deception about their true nature. Gunners received instructions on their use. The fuses required no special setting procedures. Crews simply loaded the shells and fired. The fuses would arm themselves after the projectiles left the gun barrels, and would detonate automatically when they detected the ground below or any large object in their path. For American artillery crews, the proximity fuse simplified their work enormously. No more calculating precise timings. No more adjusting settings based on estimates of range and trajectory. They could focus on placing shells over the target area, and the fuses would handle the rest. The psychological effect was significant. Artillerymen gained confidence in their weapons' effectiveness, knowing that every shell fired would explode at the optimal height. For the Germans on the receiving end, the experience was profoundly different. They faced artillery that seemed to violate the rules they understood. Shells exploded overhead regardless of visibility conditions, regardless of whether American observers could see the target, regardless of terrain that should have masked their positions. The consistency and precision of the airbursts suggested some new technology, but German intelligence had no information about what that technology might be. German soldiers began reporting strange phenomena, shells that exploded at consistent heights above ground, artillery fire that remained effective even when weather prevented aerial observation, casualties among troops who should have been protected by terrain or fortifications, Reports filtered up through the chain of command, reaching intelligence officers who struggled to explain what was happening. Some German commanders theorized that the Americans had developed improved timed fuses with more precise mechanisms. Others suggested that forward observers, perhaps using some new type of optical equipment, were calling in extraordinarily accurate fire. A few suspected that a fundamentally new technology was at work, but without physical evidence, they could only speculate. The truth would become clear only when German forces began capturing American ammunition dumps and examining unexploded shells. But by then, the Battle of the Bulge would be decided, and the proximity fuse would have contributed to stopping the last major German offensive on the Western Front. Obergefreiter Hans Müller had survived 3 years on the Eastern Front. He had endured Soviet artillery barrages at Jeff, where shells fell like rain for hours at a time. He had learned to judge by sound alone whether an incoming round would land close enough to be dangerous. He had mastered the timing of artillery fire, knowing when to keep his head down and when he could safely move between positions. None of that experience prepared him for what happened near Echternach on the night of December 25th, 1944. His company had been ordered to advance under cover of darkness, moving through a wooded valley toward American positions. The weather was miserable. Fog hung in the trees. Snow covered the ground, muffling footsteps, but also making movement visible to anyone watching from high ground. Muller and his squad moved carefully, using terrain for cover, staying in the tree line whenever possible. The American artillery opened fire without warning. Muller heard the distant boom of guns, then the familiar sound of shells in flight. He dropped into a depression beside the trail, pressing himself against the frozen earth. Other men scattered, seeking whatever cover they could find. Some dove behind trees. Others dropped into drainage ditches that ran alongside the path. Then the shells began exploding, and Muller realized something was wrong. The explosions came from above, not from impacts with the ground. Fragments showered down, striking the earth all around him, ricocheting off tree trunks, cutting through undergrowth. He heard men screaming. The soldier who had been running beside him a moment before lay motionless, struck by fragments that had come from overhead. Muller pressed himself deeper into the depression, trying to make himself as small as possible. Another salvo arrived, and again the explosions came from the air above the valley. The fragments fell almost vertically, finding men in foxholes behind trees in positions that should have provided protection from conventional artillery. When the barrage ended, Muller's squad had lost 6 men killed and 4 wounded seriously enough to require evacuation. Out of a squad of 12, only 2 men were completely unharmed. The company as a whole had suffered similar casualties. The attack was called off. The survivors pulled back to their starting positions, carrying their wounded and leaving their dead for later recovery. That night, huddled in a bunker with other survivors, Muller tried to make sense of what had happened. The shells had exploded at consistent heights, perhaps 10 to 15 meters above ground. The timing had been too precise for conventional timed fuses, especially in conditions where American observers could not possibly see the target. Some men speculated about new weapons, about American technology that allowed them to guide artillery shells somehow. An Unteroffizier who had fought in North Africa suggested that the Americans might be using some kind of radar-triggered fuse, but others dismissed the idea. Radar equipment was large, mounted on trucks or in fixed installations. It could not possibly fit inside an artillery shell. The discussion went nowhere. The men had no answers, only the evidence of their casualties and the memory of shells exploding overhead with uncanny precision. Similar conversations took place in German units across the Ardennes front. Reports accumulated in intelligence files. Interrogators questioned German prisoners captured by American forces, asking what they had observed about American artillery. The prisoners described shells that exploded in the air, casualties among troops in covered positions, artillery fire that seemed unnaturally accurate even in poor visibility. On December 26th, near Echternach, American artillery equipped with proximity fuses engaged a concentration of German troops attempting to cross the Sauer River. General George Patton, commanding the Third Army, later reported that a battalion-sized concentration of fire killed 702 Germans by actual count. The concentration had caught the German battalion in the open, crossing difficult terrain where men could not quickly find cover. The proximity-fused shells had detonated overhead, filling the crossing site with fragments. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Patton would later write to the War Department describing the new shells with characteristic directness. "The new shell with the funny fuse is devastating," he wrote. "We caught a German battalion, which was trying to get across the Sauer River, with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." The comment about devising some new method of warfare was not hyperbole. The proximity fuse had fundamentally altered the mathematics of artillery effectiveness. Troops in the open were vastly more vulnerable than they had been with conventional fuses. Foxholes provided much less protection. Movement under artillery fire became far more dangerous. The weapon's impact on German tactical thinking would prove as significant as its direct effects on casualties. But understanding why the fuse was so devastating requires understanding what happened inside those shells as they arced through the air toward their targets. The Mark 45 proximity fuse, the version used in American Army artillery shells, measured approximately 3 inches in length and less than 2 inches in diameter. Into that small space, American engineers had packed a complete radio system, a power supply, safety mechanisms, and an explosive train capable of initiating the shell's main charge. The fuse armed itself through a series of mechanical and electrical steps that began the moment the shell left the gun barrel. As the projectile accelerated down the barrel, setback forces compressed a spring mechanism. When the shell exited the muzzle, the spring released, allowing a small windmill on the fuse nose to deploy. The windmill, driven by air rushing past the spinning shell, turned a generator that produced electricity for the radio circuits. After the windmill had rotated a predetermined number of revolutions, corresponding to a safe distance from the gun, electrical contacts closed, connecting the power supply to the radio transmitter and receiver. A small vacuum tube oscillator began broadcasting electromagnetic waves at approximately 180 megahertz. The waves radiated outward from an antenna built into the fuse body. When the shell approached a target, whether an aircraft or the ground itself, those electromagnetic waves reflected back toward the fuse. A receiver circuit detected the reflected signal. As the distance to the target decreased, the strength of the reflected signal increased. The fuse used a heterodyne detection system, mixing the transmitted frequency with the received frequency to produce a beat signal. The amplitude of this beat signal corresponded to the strength of the reflection, which in turn indicated the distance to the target. When the reflected signal reached a predetermined strength, indicating the shell was at the optimal distance from the target, an amplifier circuit triggered a thyrotron tube. The thyrotron, a gas-filled switching device, could handle large currents despite its small size. When triggered, it conducted electricity from a small capacitor to an electric detonator. The detonator fired, initiating a booster charge, which in turn set off the main explosive filling of the shell. For anti-aircraft use, the fuses were calibrated to detonate when the shell passed within approximately 20 to 30 feet of an aircraft. The proximity allowed the explosion to envelop the target in fragments without requiring a direct hit. Against aircraft traveling at several hundred miles per hour, this increased the probability of damage or destruction by factors ranging from 5 to 10 times compared to timed fuses. For use against ground targets, the fuses detected the approach of the Earth itself. The radio waves reflected off the ground, and when the signal strength indicated the shell was 30 to 50 feet above the surface, the fuse triggered detonation. This height maximized the area covered by fragments from the explosion. A shell detonating at ground level wasted much of its explosive energy, creating a crater. A shell exploding in the air directed its fragments outward and downward, creating a lethal cone of steel covering an area far larger than a ground burst. The mathematics of fragment dispersion were well understood by artillery engineers. A typical 105 mm high explosive shell contained approximately 4.5 pounds of TNT and a steel casing that fragmented into roughly 1,000 pieces upon detonation. When the shell exploded on contact with the ground, perhaps half those fragments were driven into the earth, wasting their lethal potential. The remaining fragments spread outward in a rough hemisphere, dangerous to troops within about 30 to 40 yards. When the same shell detonated 40 feet above ground, nearly all the fragments traveled through air rather than earth. The explosion created a cone of fragments covering a circular area approximately 100 yards in diameter. Every fragment within that cone carried enough energy to wound or kill. The effective casualty area increased by roughly 4 times compared to a ground burst. German soldiers experiencing this for the first time could not comprehend the mechanism, but they could observe the effects. American artillery had become vastly more lethal. A single battery of guns firing proximity-fused shells could accomplish what previously required 4 batteries firing conventional ammunition. And because the fuses operated automatically, requiring no adjustment by the gunners, American artillery could maintain high rates of fire without the delays associated with setting timed fuses. The technology represented not just an incremental improvement, but a fundamental shift in artillery effectiveness. And the Germans, caught in the open during their Ardennes offensive, bore the full brunt of that shift. German military intelligence struggled to understand what they were facing. Reports from the Ardennes described artillery fire of unprecedented accuracy and effectiveness, but the mechanism remained unclear. Without physical evidence, without captured examples of the new fuse, German analysts could only theorize. The first intact proximity fuse fell into German hands in late December 1944, when a dud shell was recovered from the battlefield. The fuse was carefully transported to a technical intelligence facility where specialists disassembled it, photographed each component, and attempted to understand its operation. What they discovered both explained the devastating effectiveness of American artillery and revealed the enormous technological gap between German and American industrial capabilities. The miniaturization alone impressed German engineers. Vacuum tubes small enough to fit inside an artillery shell, yet robust enough to survive the shock of firing. A complete radio transmitter and receiver occupying less space than a man's fist. A power supply that activated itself after launch and provided sufficient electricity for the brief operational life of the fuse. The engineering was sophisticated, the manufacturing precision evident in every component, but understanding how the fuse worked provided no immediate solution to the tactical problem it created. German forces could not jam the radio signals without sophisticated electronic countermeasures equipment that did not exist in portable form. They could not shield their troops from the fragments of air-bursting shells. They could not produce their own proximity fuses, even with the captured example to study. The problem was not knowledge, but capacity. German industry in late 1944 was under relentless attack from Allied bombers. Factories were dispersed, production was disrupted, raw materials were increasingly scarce. The precision manufacturing required for proximity fuse production was beyond German capabilities even in peacetime. Under wartime conditions, with the industrial base crumbling, it was impossible. German researchers had actually been working on proximity fuse design since before the war. More than 30 different approaches had been explored, including acoustic fuses triggered by engine noise, electrostatic fuses that detected charged objects, and radio-based designs similar to the American system. None had progressed beyond the experimental stage. None had overcome the fundamental challenge of building electronics robust enough to survive gun launch while remaining sensitive enough to detect targets reliably. The captured American Fuze revealed that the Allies had solved these problems years earlier. The realization was demoralizing. German soldiers in the field were being killed by technology their own country could not match. The industrial and scientific superiority of the United States, already evident in countless other ways, had produced yet another weapon that German forces had no effective counter for. Tactical adaptations were attempted. Units were ordered to disperse more widely, reducing the number of casualties any single shell could inflict. Troops were instructed to move in smaller groups, using terrain for concealment rather than protection. Night movement, already preferred, became standard practice whenever possible. But these measures only reduced casualties. They did not eliminate the fundamental problem that American artillery had become far more deadly. The psychological impact extended beyond the immediate battlefield effects. German soldiers who had believed their military technology was at least equal to that of the Allies found that assumption challenged. The proximity fuse joined a growing list of Allied technological advantages. American radar systems were more sophisticated. American radio equipment was more reliable. American vehicles were more numerous and better maintained. American logistics delivered supplies in quantities that seemed impossible to soldiers from an economy stretched to breaking. One German officer, captured in January 1945 and interrogated about the artillery he had experienced, expressed what many of his comrades felt. The Americans, he told his interrogators, seemed to have unlimited resources and unlimited ingenuity. Every time German forces adapted to one Allied advantage, another appeared. The proximity fuse was simply the latest example of a pattern that had been evident for years but was now impossible to deny. The officer's assessment was accurate. American industry in 1944 was producing war materials at scales that dwarfed German output. The proximity fuse program alone involved more than 100 manufacturing facilities and employed thousands of workers. Production costs had dropped from $732 per fuse to $18 through manufacturing improvements and economies of scale. By war's end, American factories would deliver 22 million proximity fuses, enough to equip a substantial portion of Allied anti-aircraft and artillery ammunition. Germany, by contrast, was struggling to produce basic ammunition in sufficient quantities to meet battlefield demands. Sophisticated electronic fuses were beyond consideration when factories were being bombed, when skilled workers were being drafted for military service, when raw materials were increasingly unavailable. While the proximity fuse was making its combat debut against German ground forces in Europe, the weapon had already been proving its worth in the Pacific for nearly 2 years. The U.S. Navy had been using proximity-fused anti-aircraft ammunition since January 1943, and the results had fundamentally altered naval air defense. Japanese aircraft attacking American ships faced a wall of fire that previous generations of naval aviators had never encountered. 5-inch guns firing proximity-fused shells could bring down aircraft at ranges and altitudes that would have been impossible with timed fuses. The statistics told the story. Where conventional time-fused anti-aircraft fire required approximately 2,000 shells to destroy a single aircraft, proximity fuses reduced that number to roughly 500 rounds per kill. Against kamikaze attacks, which became increasingly common in late 1944 and 1945, the proximity fuse proved even more effective. Kamikaze pilots flew straight courses toward their targets, making no evasive maneuvers, concerned only with reaching their target ships. The predictable trajectories allowed proximity-fused shells to intercept the aircraft with devastating efficiency. Ships equipped with proximity fuses survived kamikaze attacks that would have been fatal with conventional anti-aircraft defenses. On May 11, 1945, the destroyers USS Hadley and USS Evans found themselves defending against a massive Japanese air attack off Okinawa. 156 enemy aircraft approached the small group of ships. Both destroyers were equipped with proximity-fused ammunition for their 5-inch guns. The Hadley knocked down 12 aircraft. The Evans destroyed 23 before being hit 4 times by planes that had already been set ablaze by anti-aircraft fire. After the action, the evaluation was unambiguous. Proximity-fused ammunition had been indispensable. Without it, both ships would almost certainly have been sunk. The Fuzes had allowed a handful of destroyers to defend themselves against odds that would have overwhelmed ships equipped with conventional ammunition. Secretary of the Navy James Forrestal would later state that the proximity fuse had helped blaze the trail to Japan. Without the protection this ingenious device has given the surface ships of the fleet, he said, our westward push could not have been so swift, and the cost in men and ships would have been immeasurably greater. British Prime Minister Winston Churchill, speaking of the fuse's effectiveness against German V-1 flying bombs, noted that these so-called proximity fuses made in the United States proved potent against the small unmanned aircraft with which we were assailed. The V-1 campaign, which had threatened to devastate London and disrupt British war production, was largely defeated by anti-aircraft fire using proximity fuses. Where early defenses destroyed only 17% of incoming buzz bombs, proximity-fused ammunition increased the kill rate to over 80%. The technology's success prompted consideration of how it might be applied to other weapons. American forces experimented with proximity fuses for mortar rounds, though development was not completed before the war ended. Rocket and bomb fuses were tested. The fundamental principle that a weapon could sense its target and detonate automatically at the optimal moment had applications far beyond artillery shells. But perhaps the most significant aspect of the proximity fuse was not its direct military effectiveness, but what it revealed about the nature of modern industrial warfare. The fuse represented the marriage of scientific research, industrial production, and military application on a scale that only the United States could achieve in 1944. The Manhattan Project, which produced the atomic bomb, received more attention and consumed more resources. The radar development program equipped Allied forces with electronic eyes that could see through darkness and weather. But the proximity fuse, in its own way, demonstrated American industrial and scientific superiority as clearly as either of those more famous programs. The fuse was a product of coordinated effort involving universities, private industry, and military services. Researchers at Johns Hopkins Applied Physics Laboratory and the Carnegie Institution solved the theoretical problems. Companies like Crossley, Sylvania, RCA, and Eastman Kodak manufactured components and assembled fuses by the millions. The military services tested the weapons, developed tactics for their employment, and deployed them in combat across 2 oceans. The entire process, from initial concept to mass production to battlefield employment, took less than 3 years. That timeline represented not just technical achievement but organizational capability. The United States in World War II had developed the ability to identify military requirements, mobilize scientific and industrial resources to meet those requirements, and deploy the resulting weapons in time to affect the war's outcome. Germany and Japan, despite their own significant scientific and industrial capabilities, could not match this performance. Both nations developed prototype proximity fuses. Neither brought them into production or combat use. The German soldiers who experienced proximity-fused artillery fire in the Ardennes carried the memory of those explosions for the rest of their lives. For those who survived the war and eventually spoke to historians, the proximity fuse occupied a particular place in their recollections. It was not the weapon that inspired the most fear. That distinction belonged to weapons like the rocket-firing Katyusha or the massive Soviet artillery concentrations on the Eastern Front. But it was the weapon that most clearly demonstrated the technological and industrial gap between Germany and the United States. One veteran, interviewed decades after the war, recalled that the proximity fuse convinced him that Germany could not win. The weapon itself was devastating, he said, but what it represented was more significant. If the Americans could put tiny radios inside artillery shells, if they could manufacture such sophisticated devices by the millions, if they could deploy them across Europe and the Pacific simultaneously, then what else could they produce? What other technological advantages did they possess? The asymmetry was too great to overcome through courage or tactical skill. This psychological dimension of the proximity fuse's impact should not be underestimated. Weapons affect morale not just through the casualties they inflict, but through what they reveal about relative capabilities. German soldiers in late 1944 faced mounting evidence that their opponents possessed overwhelming material superiority. The proximity fuse added to that evidence in a way that was both immediate and undeniable. For American forces, the fuse provided confirmation of their industrial and scientific advantages. Artillerymen who fired proximity-fused shells gained confidence in their weapons' effectiveness. Infantry who advanced under the protection of proximity-fused artillery fire understood that their supporting fires were vastly more capable than those available to the enemy. The cumulative effect on morale was significant. The technology survived the war and evolved into the guided munitions and smart weapons of subsequent decades. Modern artillery shells equipped with GPS guidance and proximity fuses can strike targets with precision that would have seemed like science fiction to the artillerymen of World War II. Anti-aircraft missiles use radar or infrared proximity fuses to detonate near their targets. The fundamental principle established in the 1940s that weapons can sense their targets and react automatically has become standard in modern warfare. But the World War II-era proximity fuse retains historical significance beyond its technical achievements. It represents a moment when the nature of warfare changed, when electronics became as important as explosives, when the factory became as critical as the battlefield. The Manhattan Project demonstrated that science could create weapons of unprecedented power. Radar showed that technology could extend human senses beyond their natural limits. The proximity fuse proved that intelligence could be embedded in individual munitions, making each shell more effective than entire batteries had been just years before. The German soldiers advancing through the Ardennes in December 1944 expected conventional artillery fire. They expected shells that would explode on impact or after timed delays. They expected to use terrain and fortifications to protect themselves, just as soldiers had done for generations. What they encountered instead was artillery that exploded overhead with mechanical precision, that functioned regardless of visibility or observation, that killed men in positions that should have been safe. That moment when the first proximity-fused shells detonated over German positions was more than just another combat engagement. It was a revelation of technological disparity. It was evidence, delivered in fragments of steel and high explosive, that the war's outcome was determined not just by the courage of soldiers or the skill of commanders, but by the productive capacity and scientific capability of nations. The Germans had launched their Ardennes offensive, hoping to split the Allied armies and force a negotiated peace. Instead, they encountered artillery fire that embodied everything they were fighting against: American industrial might, scientific innovation, and the ability to translate research into battlefield weapons faster than their enemies could respond. The proximity fuse did not win the war alone. No single weapon did. But it contributed to victory in ways both direct and symbolic, killing enemy soldiers efficiently while simultaneously demonstrating the technological and industrial superiority that made Allied victory inevitable. For the men on both sides who experienced its effects in combat, it was unforgettable. For historians examining World War II's technological dimensions, it remains one of the war's most significant innovations, a weapon that changed not just how battles were fought, but how armies understood the relationship between science, industry, and military power. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.